Hello everyone, welcome to Tan45Engineering. We are here with yet another video in our mastering data structures and algorithms in Java, and today's topic is quicksort. Let's get started. So quicksort is a highly efficient sorting algorithm that uses the divide and conquer just like merge sort. It's known for its average case time complexity O of n log n, just like merge sort, though the worst case is O of n square. Though with careful implementation it performs very well in practice. It's an in-place sorting algorithm. Unlike merge sort, it doesn't require extra space. It is unstable sorting algorithm, again unlike merge sort, so it does not preserve the relative order of equal elements. You are aware of what is the relative order of equal elements from our previous video. It follows the divide and conquer, that is it breaks down the arrays into smaller partitions around a pivot until the last single elements are left. Okay. What is a pivot and all, I'll go through it. So let's say we will take an example. Let's say we have 10 7 8 9 1 5, right? So each time what it does, quicksort, is it picks a pivot. Okay, it picks a pivot, let's say 1. Okay, and all the numbers that are smaller than 1, or let's say it picks 8 as the pivot. Okay, I'll say it is the pivot. That means 8 will be here. All the numbers that are smaller than pivot, 1 7 and 5, will come before the pivot, and all the numbers bigger than pivot will come on the right side, 9 and 10. Okay, now after this it will internally sort the left side and the right side as well, not internally, recursively. Okay, so we will come to this. Okay, but easier to remember, quicksort is the one that always picks a pivot. Okay, so let's see how quicksort works. Okay, no, the input was okay. Okay, so this is our input, 10 7, or I'll remove them and write 10 7 8 9 1 5. Okay, and of course the expected output is 1 5 7 8 9 and 10, right? Okay, now let's follow the steps and try to solve this. Okay, choose a pivot, select an element from an array as the pivot. So you can actually choose any pivot. Various strategies can be used, like some people use the midpoint, selecting midpoint as a pivot, or a random number, or second element, first element, or the last element, like selecting the first, last, random element. Okay, so we'll pick last element as our pivot. So every time we'll be picking last element as our pivot. Okay, now partition, rearrange the arrays so that all elements less than pivot are made to move to its left, and all elements greater than the pivot are moved to its right. Okay, so we will follow a strategy. What we'll do is, let's say in first pass we pick the pivot, 5 is our pivot. So one by one we'll compare 5, that is our pivot, to all the rest of the elements. If the element is less than 5, we'll move it to the start, otherwise in the end. Okay, so 10 will be compared to 5. 10 is bigger, so no movement. 7 is also bigger than 5. 8 is bigger than 5. 9 is bigger than 5. 1 is smaller than 5, right? So we will swap 1 with our starting index. So let's say we'll keep some index for there. So we'll have 1 index for keeping the position on where to move. Then we have our pivot, which is 5. Okay, now once we move, so 1 and 10 will get swapped, so it will be 1 7 8 9 10 5. One more index that is actually traversing through this, so we need another index. Let's say index 2. Okay, now once it has reached 5, or the end of the array line, we know no more elements are left for comparison before 5. Now 5 will be moved to its correct position, since all these elements that have not moved are bigger than this. So for index 1 plus 1, this will be the position. and 5 will be swapped with this position. So we will get 1, 5, 8, 9, 10, 7. Okay, so we'll return this position to the next one, and now we want to perform again. Okay, so all elements less than the pivot are moved to its left, all elements greater than the pivot are moved to its right. That is correct, right? All the elements on left are smaller than 5, all elements on right are greater than 5. So up till here we are sorted. Okay, now recursive sorting. Recursively apply the same logic to the left and right partitions. Combine once the base case is reached, that is sub arrays of one element, the array is fully sorted. Okay, so now we'll have to apply the same logic on the left hand side and on the right hand side. So when we'll apply on the left hand side, nothing will change, 1 and 5 are still sorted. We'll apply it on the right hand side. Okay, so we'll remember the indexing, since it is in place sorting, we are doing the swaps, we do not use extra arrays. So we'll remember the indexing again for this one, 8, 9, 10, 7, 1 and 5 are still there. Okay, 7 will be picked as the pivot, 8 will be compared to 7, it is bigger, 9 will be compared to 7, it is bigger, 10 will be compared to 7, it is bigger. So 7 will get swapped with our first index. First index will again be here at the start, so these two will swap. Next line will get 1, 5, that is already there, and then 7, 9, 10, 8. Okay, now we return back on the 7. So, since this was the midpoint or the pivot, all the elements on the left hand side are already sorted. All the elements on the right hand side will call the quick sort again. So for these elements, again 8 will be picked up as pivot, the last element. 9 and 10 are compared, there is no movement. 9 and 8 swaps with each other, it becomes 1, 5, 7, 8, this is pivot, 9, 10. Up till here we are fully sorted. Again 10 is picked as the pivot, and 9 and 10 both are already sorted, so there will be no movement, and final output would be 1, 5, 7, 8, 9 and 10. But how are we going to do this in code? This is easier to understand from here, but how are we going to achieve this in code? Okay, so let's go to the code and let's solve this. So we need two things, we need the quick sort and we need a algorithm to partition them and get back, because we have to call recursively on the left hand side and the right hand side of the subarray, just like the merge sort. So we'll say this will be our main function to perform quick sort. Okay, so public static void quick sort, it will accept our array, then the indexes int low, int high. Okay, now if low is less than high, so this is how long we have to do the partitions inside. We'll say find pivot element so that elements smaller than pivot are on the left and bigger elements on the right. Okay, so we'll say int pivot index, we'll call another method partition, will pass it our array low and high. Okay, then we are going to call quick sort recursively on the left half and the right half. So we'll call, sorry, we'll not call directly, recursively sort the left and right sub arrays. Okay, so we'll say quick sort will pass the original array low, but the high would be pivot index minus 1. Okay, again quick sort will pass the array, now the low would be pivot index plus 1 and high will remain high. Okay, Now we need to work on the partitioning algorithm. The job of the partitioning algorithm is going to be to make the difference, to make the pivot, and perform this swaps as well. So the role of partitioning algorithm here in this example would be that it sorts them. So 1, 5, 8, 9, 10, 7, the array becomes like this, and 5, the index of 5 is returned to us as the pivot. So we'll call the quick sort on the lower half, the left hand side, and the right hand side half again, because 5 will now be at its correct position. Okay, that's why we are not considering the pivot index -1 and +1. Okay, so we'll say private static int partition, it will take array int low int high. Okay. So we'll need the pivot int pivot is equal to array of high, just like how we did here. 5 was picked as the pivot, so every time the last element, the biggest element is or the last index element is being picked as the pivot. So you can use any strategy, you can pick the first element, the mid element, it is up to you. We are picking the last element. Okay, so int pivot is equal to array of high, so we'll just say choose the last element as pivot. Okay, now int, we need one variable, I is equal to low -1, so we'll keep it lower than the current pointer. This will be pointer for smaller element. So we the index 1, that is the pointer which is actually keeping track of where to make the swaps, that will be our I. Okay, where are we? Okay, now we'll make the movement. So another pointer which will traverse through the left half until the pivot point, that will be int j is equal to low, y equal to low, and not starting from 0, because when we'll be performing let's say quick sort for the right sub array, 8 0 1 2 2 will be the lower index and 5 will be the higher index, so we'll be making changes only on the right partition. Similar way, if there were more values on the left hand side, let's say there were 2 3 0 values as well, that will be on the left hand side. We'll have the low as 0 and the high as the index of 1, right? Okay, so in j is equal to low, j is less than high, j plus plus. Okay, so we are going to traverse one by one. If any element is found, if array of j is less than pivot, right? If the element is smaller than the pivot, like we did the comparison here, is 10 smaller than 5? No. 7 smaller than 5? No. 8? No. 9? No. 1 is smaller than 5. So the moment we find 1, we swap it in the first position. That will be our I index. Okay. So we'll say if this happens, I plus plus, so now I will now be at the lower point. Swap array of I and array of j. So we'll say int temp is equal to array of I is equal to array of j, and array of j is equal to temp. Okay, right? So this logic here, this makes this swap that we did for 1 and 10. Okay, now our swap is done. In the end, the pivot is still in the end, right? So we have to move pivot also in the start position at 5th, that is one position above our I index, correct? So we'll make that change as well. So once the for loop is over, we'll say swap array of I plus 1 and array of high, that is pivot. I'll say or pivot. Okay, so we'll say int temp is equal to array of I plus 1 and array of I plus 1 is equal to array of high. In the end, array of high is equal to temp. Okay, and we have to return the index. So what is the index? I is pointing at 1 and fifth is here, so I plus 1. This is the index of our pivot. So return I plus 1. Okay, this will be return the partition index. Okay, now if you go back, we get here our index, and now again quicksort will be called on the lower half, and then the quicksort will be called on the right upper half as well. So recursively calling the quicksort till the last value will sort our overall algorithm. Okay, so let's call int array is equal to 10 7 8 8 9 1 5. Okay, int n is equal to array dot length. We'll call quicksort, will pass array lower index 0, upper index n minus 1. Okay, in the end system dot out dot println sorted array, and then for loop to print the array, int element from array system dot out dot print element plus some space. Okay, so I'll run this 1 5 7 8 9 10. Okay, and now our array is sorted using quicksort. So that's all. That's how the quicksort works, and that's how you solve a quicksort problem or a problem on quicksort. Okay, we'll move next. In summary, yeah, time complexity is O of n log n. Yes, we did consider that the worst time complexity possible is O of n square, but most cases the time complexity is considered for quicksort is O of n log n. Space complexity, actually it is a in space sorting algorithm, so does not require extra space, but since it calls recursively it is calling the smaller half and the bigger half, it uses memory on the logarithmic scale. So that's why O of log n auxiliary space is used for the recursive stack calls. Okay, and of course there are few differences between quicksort and merge sort. Quicksort is in place, it is faster in practice than merge sort actually. It has a worst case time complexity of O of n square, but in practice quicksort is faster than merge sort if you define a better pivot strategy. Merge sort is stable, it guarantees n log n time complexity. So merge sort is sure that every time the time complexity will be O of n log n, though in case of quicksort it could be O of n square at times time complexity, but it requires additional space, that is O of n. It requires O of n extra space for the arrays. Okay, so that's all from today's video everyone. If you have anything, please let me know in the comment section. In the end, please like, share and subscribe. Thank you.